before I begin, it never occurred to me that assigning a problem set due the day after an election would be problematic, and I regret it now in retrospect, and probably won't do it again. But just it's too late in effect to but any of you who are still working on the thing, I'll accept it as on time, even if it's not on time. The other thing is it's a physics class, and so I normally stick entirely to physics, but just my whole adult life and certainly my entire time here at the university, I've worked towards trying to build community, inclusiveness, integrity, social justice, and I have no plans on changing that, whatever, come what may. If any of you have things you want to talk about, come and talk to me. I'd be happy to talk to you about them. All right? On to physics. So, talking about insulation, in fact, how you limit the flow of heat rather than encourage it. Clothing and insulation are both have that in mind. And I said last time that reducing, trying to reduce the flow of heat involves trying to suppress all three of the heat transfer mechanisms. Suppressing the transfer of heat by conduction typically involves using materials that are not good at conducting heat. That means probably staying away from the metals, because metals typically are good at conducting heat. So we don't wear metal clothing usually. The next, I'm thinking of people wearing aluminum hats. Sorry. Over the years, I've had people, okay, having well thought of that and not being able to unthink that thought, I have had people in the past, the aluminum hat folks, contact me about how to prevent evil forces from reading their minds and stuff like that. It's always an interesting experience. I have learned not to get too deeply involved in the conversations. These are by email typically, because they never really end well. They often end with, I suggest that you go and see your doctor to assess the injury you're experiencing and hope that they get proper mental health care. Okay, anyhow, sorry it was a long night. So controlling the flow of heat. Stay away from the metals. Even the solids that are the insulating solids are not so great for controlling heat. It turns out the gases are even the worst of the bunch for conducting heat. And so air is a terrible conductor of heat. If you're requiring the heat to go atom by atom, in a sense, through the gas, don't allow the gas to move, because then you got convection, which is pretty good. But make the heat go. This local patch of air conveys heat to that local patch of air, which conveys it to that, and so on through the material. It's terrible. Air is not the worst of the gases. All the gases are not particularly good. It turns out the low mass ones, like helium, are better. Helium's a decent conductor of heat. It gets worse as the mass of the particles gets bigger. So things like argon, which is a heavier atom, a fairly common in the atmosphere, atom that's larger than air, is a worse conductor of heat than air, and so it's often used as insulation when given the choice. We use argon instead of air. You can go heavier still, but then it gets very expensive. Things like krypton and xenon, the heavy noble gases, are even worse conductors of heat than argon, but they're very expensive. So, and neon would be a bad choice because it's lighter and it's expensive. So, you'd be shooting yourself in the foot. All right. So gases, bad conductor of heat. They do, however, undergo convection. So if you're going to use a gas as part of the insulation, that now you have to suppress convection or make it poorly functioning. And the classic way to do that is to trap the gas in a fibrous or bubbly environment, so that it acts. It can't move. It can't convect. And I was showing you last time as a fiberglass is a very common insulation in houses. It's a fiber system. It's glass fibers. It's not something you would want to wear because it's itchy, and it's probably not great to be in contact with it extensively. But it's nice in houses, and so most modern houses, when they're built, they have blankets of fiberglass built into the walls, and particularly into the ceilings. It turns out that the ceiling is much more important than the walls because convection lifts heated air up, and heat convects out of your attic and roof very, very easily in an improperly insulated house. So putting a really heavy blanket of fiberglass in the attic is a good idea. I also talked about styrofoam and other foams are popular now as insulation as well. They also trap gas and make it so it can't convect, and therefore are great insulators. Installations like that are often rated in this R value, and the bigger the R value is, the more insulation you get. And modern energy efficient houses have these big R values in the walls and the ceilings. Just for fun, these are fire bricks. They are it looks like it's a ceramic brick, but it's a very light, fluffy ceramic. It's not using the ceramic so much as the insulation, although the ceramic itself is not a good conductor of heat. But it's also filled with empty spaces, which presumably have gas. It's a porous material. It doesn't trap. It's not closed bubbles. If it were closed bubbles of gas, and you did what I'm about to do, which is to hold a torch up against it, I can heat parts of it red hot. You see it's red? And my hand's fine. If it were closed bubbles of gas like styrofoam, we'd have a different problem. As you heat up a trapped portion of gas with a fixed volume, what happens to its pressure? Increases. You blow the bubbles up. So they can't use a closed bubble in this if it's going to be used in a fire environment where the temperature goes up by huge amounts. So it's open bubbles. That does mean air can work its way through, but it's really hard. And so the heat has a terrible time going through all the air pockets. It's a good insulator. All right. So I'm back to that question I asked you last time about which is a better insulator, a sweater that weighs 5 pounds or a sweater that weighs 10 pounds. Everything else being identical, same thickness. For example. It's actually the lighter one that's the better insulator. And you may have encountered this if you've bought down clothing, down coats or quilts. They're often sold as sort of the volume in which a certain portion of down occupies. I forget how this is done exactly, but you can get it wouldn't be a kilogram, but okay, let's say a kilogram of down. You can buy a couple of different downs. You buy the kilogram of down that occupies this much volume, and you buy the kilogram of down that occupies this much volume. This one's the better insulator. Why? Because it for the same mass and weight, it traps more air. And so if you fill your coat, your down coat, with the one that occupies this much space, and you fill another down coat with the down that occupies this much space, the two coats look the same. The one coat weighs less than the other because its down fills more space, ties up the air, and the heat can't go through. There's less down through which the actual down itself, the physical down through which the heat can flow, is reduced in the one that weighs less. It's a better insulator because you don't actually want the down isn't the insulator. It's the trapped air that's the insulator. So don't put any more down in it than you absolutely need. More is not better. Is that okay? All right. Why did I ask this question? I can't remember exactly. So you're sitting in a 150-degree sauna. I mean, this is sort of, and it's feeling pretty hot. If you now start waving your hands around, if you turn on a fan, do you feel cooler, same, or hotter? Do you understand the question? If you stir the air around, how does that affect what you feel? How many think that it feels the same as before? How many think that it feels hotter than before? How many think it feels cooler than before? It's tempting to think that it would make you feel cooler because you're used to that when you turn on a fan, you feel cooler. No, you're going to feel hotter in this case because when you're just sitting there in the sauna or anywhere, you accumulate a layer of air near your skin that has the temperature approximately of your skin. Producing that layer of air involves heat transfer. So if the air started very cold, you will have to have given it heat to warm it up to your skin temperature, and you will have felt cold for a little while, but less so now because you're surrounded by warmed up air. If it was really hot outside, you will have felt hot briefly, but now you'll feel less so because you will have cooled down the air near your skin to about body temperature. And now you've got that layer on you, and you're good. If something blows that layer off, then you've got to go through the whole process again. So if it's cold outside and this warmed layer is blown off of you, you have to warm it again. You feel cold again. And then it gets blown off. You get feel cold again. That's wind chill. If you ever wonder what's wind chill about, it's the fact that you accumulate warmed air near your skin. If it's really close, it's experiencing viscous drag. It doesn't convect well. It's the layers farther away that convect. So you are aware of this, not thoughtfully, now maybe thoughtfully, but you know that if you stay still in really cold air, or really hot air, or cold or hot water, same thing, even more so. When you go in cold water and it's really cold. Okay, now I'm getting used to it. Sort of, when you start moving, you feel cold again because you have removed that layer of warmed water from your skin. And actually, wetsuits then try to keep that layer on the surface of your skin so you can't lose it. So you warm it up only once. Okay, so wind chill is, you experience wind chill when the environment is cold around you and the wind turns on and blows away these layers of warmed air off your skin and make you warm a new one, and a new one, and a new one, and a new one. All right? This is a case of wind, not chill, wind anti-chill, or I don't know, wind cook. If it's windy and the air is really hot, you keep cooling down air and you lose it. And you cool down air and you lose it. And you cool down air, and consequently the heat transfer to you is unpleasant. Okay? So you tend to stay warm or cool, to keep the temperature under control. Don't let the air go away. And that's part of what clothing does for us. It traps air near our skin, so we can't. So once we have warmed it up or cooled it down to a comfortable temperature, it's harder for it to get blown away. So that's why a windbreaker, for example, just a simple thin nylon shell wrapped around you, which by itself is there's no serious insulation there. It just keeps the wind from managing to rip off this layer of comfortable tide air. Technical word. All right. Okay, so hopefully you got a sense for ways to keep the conductive and convective flow of heat under control. How about thermal radiation? Well, I've already told you about thermal radiation follows this law known as the Stefan Boltzmann law that has the 4 parts. It's got emissivity, how good the surface is at emitting its own thermal radiation. The Stefan Boltzmann constant is just a constant of nature. Temperature on an absolute scale to the 4th power, and finally how much surface you're dealing with. So if you want to avoid losing heat yourself, it turns out we radiate a lot of heat off. I've done this calculation so many times. I think we radiate about 800 watts of thermal energy off of our skin. And it's in that ballpark, which is that's a lot of radiant power. If we get back 800 watts, for example, by having everything around us at the same temperature as our skin, everything around us is sending thermal radiation back at us as fast as we're sending it out, we don't have any net loss, so it doesn't matter much. But if you were to walk outside with nothing on a bitter cold winter day, the stuff around you is radiating at you relatively weakly, you're radiating brightly, you're going to lose several hundred watts of body energy. Watts is a unit of power, it's energy per second. And you'll feel really cold. simply because of thermal radiation. So one of the tasks of clothing is to control the thermal radiation. And by having clothing in contact with you that's pretty much the same temperature as you and the clothing are exchanging thermal radiation, and you don't lose much. So actually having multiple layers of clothing, it turns out that if you have a series of layers on you, one after the next, as the temperature goes down with each layer and finally drifts off towards body temperature, towards outdoor temperature at the outermost layer, that sequential drop in temperature and the thermal radiation between those, it significantly reduces the heat you lose by thermal radiation. Multiple layers is a good way of insulating things. And actually some systems are insulated with layer after layer of very, very thin material that is in fact often reflective. There's a material known as super insulation, which is just thin as, it's crazy thin plastic, so that it's fragile and stuff. You wouldn't want to really try to do anything with it. But you put it in there like, it's like you're making a Napoleon, one of these pastries that has like 1,000 layers in it. It's all those layers, the flow of heat then through those layers by radiation is just terrible. And so it makes for very good insulation. Anyway, this is why multiple layers is useful. One of the reasons multiple layers in clothing is useful to try to prevent you from getting cold in a cold day or hot on a hot day. Suppressing thermal radiation. If you can, use materials that are shiny, because shiny materials, okay, I play with this, they cause both sides of the shiny material to see reflections of themselves. So if you've got a hot thing, if it's a hot day outside, and you go outside and you put aluminum foil around yourself, again, assuming the guys with the butterfly nets don't come and get you, you see a reflection of your own thermal radiation, and so you feel warm. And the great outdoors, which I think I said was cold, sees a reflection of itself. Or if it's hot, it doesn't matter, it sees a reflection of itself. And I can show you that. Right now, this temperature sensor, this bolometer, is seeing the glow from this warm black surface. But if I insert a piece of aluminum foil between the two, the thermal radiation drops dramatically. The bolometer, that temperature sensing widget, is seeing the reflection of the bolometer. This is cold, bringing it to room temperature. So it says, hey, there's nothing hot over there. I can't see it. It sees a reflection. And similarly, this guy radiating thermal radiation goes right back at it, so it doesn't feel cold. If this was you, you would feel cold, sending your heat towards the bolometer. Anyway, that breaks the connection. Each thing sees its own reflection. Okay? I've talked about this one before, but if you open the door of a freezer and stand in front of it, so there is cold air pouring out of the freezer toward the floor. You put something that makes it visible, mist, you'll see it dropping down there. So you're not in that cold air, but nonetheless you feel quite cold when you stare at it. And that's because, and okay, I'll ask the question because it's fairly straightforward, I hope. How many think, A, you're radiating more heat at the freezer than it is at you? How many think it's radiating cold at you? Good, there's no such thing as radiating cold. Cold isn't an active thing, it's a lack of radiation. Now, you're radiating less heat than normal when you stand in front of the freezer. Only if you're bored. And how many think you're radiating more heat than normal when you stand in front of the freezer? Your radiation doesn't increase because there's a freezer in front of you. Your radiation is just based on your temperature. So D it's not D. It is A. It's that you're radiating it at your temperature, which is hot, more or less. And the freezer is radiating you at its temperature, which is much colder. And that radiation goes down by a factor of the temperature to the fourth. So it doesn't take a big drop in temperature into that freezer for it to really stop radiating significantly. Consequently, you lose much more to it than it does to you, and you have felt this in the past. You're not usually totally exposed unless I don't want to know what you were just doing. But your face and your hands will go up near it, and you can feel even on your face, wow, that's kind of cold, as though it were sending something rejected choices. You want to wear white or you want to wear shiny, silvery metallic. It turns out that white typically isn't good enough because a white surface might be white in the visible, but it's rarely white in the infrared. And therefore, it's usually more black than you like. So wearing a white clothing or white deck or something when you're fighting a fire is just as problematic as wearing a black something. Shiny, metallic. And so firefighters, when they go off to deal with firefighters, particularly in the west, along the west coast, and every summer these days, it's firefighter land. They carry with them emergency equipment in case they get overtaken by a fire, which alas happens. There have been some famous cases when a lot of firefighters have been. The Man Gulch case was a terrible one. People were actually, a number were killed way back. They carry with them emergency kit. And the emergency kit includes an aluminum tent. The issue is you get rid of all the combustible material on the ground. You go as low as possible. Why do you think you want to go low? What kind of heat transfer are you trying to suppress? Convection. Convection carries heat naturally upward. So if you go below the fire, convection doesn't manage to take heat down well. So you go low, get rid of the burnable stuff, because obviously you don't want to be part of the fire. And you don't want to touch the tent because you don't want conductive heat transfer. And you don't want radiative heat transfer from the flames overhead. They'll be sending thermal radiation at you in the tent ferociously. You want them to be reflected away. And so those tents are life-saving in a forest fire. Any questions about that idea? They're not the be-all and end-all, but they're better than nothing. This is more discussion of the spectrum of thermal radiation. Something I've never really shown you in detail, but it's worth doing. The book has always had this, but the thermal radiation spectrum, that is the mix of frequencies and wavelengths of electromagnetic waves that come off of the surface, depends on the temperature of the surface. If the surface is black, true black, which means it's as good as possible at absorbing light and emitting its own thermal radiation, the constituents of the surface don't matter. The spectrum of light that comes off of it is determined entirely by mathematics and simple physics. And it depends on temperature. And so if the temperature of that surface, of that black surface, is about 5,800 Kelvin, which is about 5,500 degrees Celsius, pretty hot. You know, it's like 10,000 degrees Fahrenheit. This is the spectrum of thermal radiation. So horizontally, this is in units known as interesting wavelength, which is related inversely to frequency. The details actually don't matter so much. These are long wavelength waves. The infrared light. This is the light we can't see because it's off the red end of the spectrum. Over here is the light we can't see because it's off the violet end of the spectrum. It's so-called ultraviolet light. At the temperature of the sun, a black body at the temperature of the sun. Black body meaning it's black and perfect, it's perfectly efficient in emitting its thermal radiation. The constituents of the body don't matter. Black bodies are all the same as far as thermal radiation. It has a fair amount of infrared light, but it's brightest in the visible. It peaks somewhere around the green. And then it continues on to the ultraviolet and then stops. This spectrum comes from the sun. The sun is essentially a black body. It doesn't look black, right? Because I told you that what defines black? Black is any light that hits it is gone forever, and that is the case. If you go visit the sun and shine a flashlight at its surface, which is kind of fuzzy because it's a gaseous surface, that light's gone. You'll never see it come back. It's jet black. And the fact that it's jet black doesn't mean it doesn't emit light. It just means it doesn't return any that you send at it. And it's actually very good at emitting light. And because it's so hot, remember that the thermal radiation power goes as the fourth power of absolute temperature. It's glowing like crazy, as bright as can be. And so it sends all this light at us. That is what's coming to the Earth. That is what you see, is the sun's thermal radiation. It's going right through empty space, doesn't need any air or anything in between. Off it goes, and we see it. And it includes mostly visible light, but it also includes infrared. And the fact that it includes infrared explains this observation that we had earlier in the class, that white cars in the bright sunlight get pretty hot. They're white. Well, yeah, they're white, meaning that they reflect this portion of the sun's thermal radiation nicely. But in the infrared, woo, they're not white, they're black. They absorb it anyway, and therefore get hot. If you really want a car that doesn't get hot, make it metallic. Not paint metallic, but like really metallic, like have it chrome plated. You'll look really cool going on the road in this shiny mirror car, but it will not get hot in the sunlight. Okay? The ultraviolet light out there is associated with sun tan and burn. Be careful of it for reasons you know already, hopefully. Yeah?
Would it be enough just to strip the paint from the car?
Would it be enough to just strip the paint from your car and just go with the metal surface that underlies it? Assuming it's a metal car, not all cars are metal anymore, right? That would be helpful. As we saw here, this surface is metal, but kind of ground so that it's not shiny, and it's dimmer than black, and dimmer than white. It is trying not to emit thermal radiation, but the shiny side, which is over here, is even better at not doing it. So yeah, you might strip the paint and then polish it up. All right. A reason to show you this is an incandescent light bulb, which again they're going the way of the dodo bird. If you could heat something to the temperature of the sun's surface, basically 5,800 Kelvin, it would glow just like, and it was black, it would glow just like the sun's surface. It would make a rich sunlight white, what we see as sunlight white, and most of the energy would be in the visible, some in the infrared, some in the ultraviolet. We can't do that because that's really hot. You can make things that hot, but they're not going to stay solid. And so what do? You have to run, if you're going to try to make light with heat, with hot objects, so-called incandescence. That's what incandescent means. Is hot enough to emit visible light as its own thermal radiation. You're not going to get the right spectrum. So this is 2,700 Kelvin. That is the temperature of a typical incandescent light bulb filament. That's as hot as you can run it without making the light bulb filament give it a short life. Because of sublimation, remember sublimation? Tungsten is the best choice for avoiding sublimation. Carbon actually melts at a higher temperature than tungsten. However, carbon sublimes a lot faster than tungsten. So carbon and tungsten, they had a battle for a while as to which would be the winning filament. Tungsten won. But even so, tungsten filaments have sublimed fast enough that people who have had incandescent light bulbs in their houses know you have to replace them every so often. And it's not so, it's more often than you like, particularly for the one that's like up here on the ceiling or something like that. So, those filaments are too cold to emit properly in the visible spectrum. They produce a lot of red light, not so much here in the yellows and greens, and they're pretty dim in the blues. So, household incandescent lighting, which you may still have around, is missing a lot of the blue that makes sunlight, gives it its real whiteness. And you can't do anything about that. They're just short on blue. And the result is the light's kind of orange if you really look at it and think about it and compare photographs and stuff, or have simultaneously an incandescent light bulb and the outdoor sunlight. You realize, whoa, they're not the same. The incandescent bulb is missing a lot of the blue. But even worse, it's emitting a huge amount of infrared light that you can't even see. And you're still paying for electric power to produce that infrared light, but it's of no value except as heating. And therefore, incandescent light bulbs are energy inefficient, and that's why they're being phased out. And it's not just that they're relatively short-lived, but also that they just gobble up electric power without producing very much light. You you can do better now with, particularly with LED lighting. In a couple of years from now, this will all be LED. It's now fluorescent, but fluorescent's a lot better than incandescent, but it has its own issues, like that lamping out. They don't live long enough either, for interesting reasons, and I used to talk about them. I guess I still do, but they're going. Anyhow, how about you? Your skin temperature is somewhere around 307 Kelvin, and I had to do it. This is a different scale. Visible is way off over here. This is all in the infrared. You emit no visible light. It's all infrared light. And there it is. It peaks out at pretty far at the infrared. Okay? Beyond that, it's all about detail. So that brings me to the final topic for this section, and one that's actually, okay, politics is, it's not a political issue so much as climate change, used to be called global warming, now it's more generically called climate change. It is real already. I mean, over the course of the time I've taught this, it has gone from being something out in the future to something happening now. We're really already seeing it. And the science is in. It is happening. It is human-produced in large part. There is still a tendency to deny it or pretend it's not an issue. It's an issue. It's going to be a big issue in your lives. We can go there. In your lifetime, there are going to be cities and countries even that become uninhabitable. Unless you want to have the scuba suit on, for example. And so you might as well understand why the production of the so-called greenhouse gases is inevitably leading to an increase in the average temperature of the Earth. And at this point, I think I've given you enough information to do that. I can now build on the pieces we've done up until now and give you an explanation. So here it is. The sun is a very hot object emitting thermal radiation, and the Earth is sitting off in the distance receiving a certain fraction of that. So the Earth is receiving a fairly specific amount of thermal radiation measured in watts that hit the Earth. And it's coming in nice and steady with tiny, tiny variation. So that's the input of heat to the Earth. And if that were all that was happening, was the Earth was accumulating this thermal energy, it would get hotter and hotter and hotter with no end in sight. I mean, yeah. But that's not the only thing that's happening. The Earth is also giving away heat to space, and it does this in all directions, and it does it by way of thermal radiation. Beyond the Earth's atmosphere, there's nothing out there, so it can't go away by convection or conduction. It has to go off by thermal radiation. So the Earth is receiving heat from the sun by thermal radiation, and it's emitting heat into space by thermal radiation. There's a difference in temperature, though. The sun's thermal radiation is coming in as emitted by an object at about 5,800 Kelvin. The Earth's thermal radiation is going out as an object at a much lower temperature. And the question is, what is that temperature? It turns out that if that temperature is minus 18 degrees Celsius, which is cold, at that temperature, if that surface is black and at minus 18 Celsius, the whole Earth, some surface associated with the Earth, is at that temperature and that size, the Earth size, the heat that goes out into space will balance the heat coming from the sun. And the Earth won't get hotter or colder. So that's essentially what happens. Is once the sun was active and the Earth was there, the Earth heated up until its effective black radiating surface, which we'll talk about in a minute, had reached 18 Celsius, minus 18 Celsius. If it were colder than that, it wouldn't radiate enough heat, and the sun would warm it up. If it were hotter than that, it would radiate too much heat, and the sun wouldn't make up for it, and it would cool off. So it's reached equilibrium at that point. You okay with that idea? That there's a certain temperature the Earth has to get to balance the heat coming in from the sun with the heat going out by thermal radiation into space. Space sends virtually none back, because the effective temperature of space is really, really, really cold, just above absolute zero, which is itself an interesting story, but it's not worth here, not the point here. Okay, if there were no atmosphere on the Earth, that balance would be struck when the Earth's surface reached about minus 18 Celsius. Because the Earth's surface would be the surface that radiates that thermal radiation. Pretty simple. And it would be very cold. The Earth would be cold. We have to be walking around in, I call them moon suits, except they'd have to be Earth suits. We walk because no atmosphere. We need some to breathe. There's also the issue of what color the Earth is. It's not exactly black. In the infrared, at its temperature, it's pretty black, though. But it's a little bit iffy, a little imperfect. All right. So that said, without an atmosphere, it will be very cold down here. So what's the problem with thermal radiation and the temperature of the Earth? Well, it's not the Earth's surface that does all the radiating. Because we have an atmosphere, the atmosphere is involved in the thermal radiation of the Earth. And if you look at air looks pretty transparent here in the visible, but in the infrared it's not so transparent. It's got a lot of features in it aspects in it that emit thermal radiation in the infrared. They have to be relatively complicated molecules. It turns out oxygen and nitrogen are so simple, being what are called diatomic molecules. You only have one pair of nitrogen or a pair of oxygens. Those are very bad at emitting infrared light, having anything to do with infrared light. But the more complicated ones, like carbon dioxide, water, all the hydrocarbons and nitrogen oxides, those interact with the infrared nicely. And if we could see in the infrared, we would see them. You would see, for example, carbon dioxide coming off of a glass of soda or one of your other favorite beverages. The carbon dioxide coming off of that would appear dark because it's good at emitting and absorbing thermal radiation, certain ones. And my dream one day is to have an infrared camera that can see that, because if you look online, you can see that. If you use a smokestack, you'll see this plume of black, infrared black carbon dioxide and stuff coming off. Anyhow, so the Earth's atmosphere does interact with thermal radiation, and as a result, the surface that is effectively emitting the Earth's thermal radiation to balance the sun's input, that surface is not at ground level. It's about 5 kilometers above ground level. The Earth's atmosphere is emitting a good fraction of the Earth's thermal radiation, not the ground. It's a mix. Certain wavelengths of light, certain portions of the spectrum come right from the ground, go right through the atmosphere. Other portions don't. The atmosphere is too opaque. It's black for those wavelengths, that part of the spectrum, and the light comes from much higher. So, light's coming in from the sun, thermal radiation is coming from the sun. It's being balanced by thermal radiation being emitted by the Earth at a level that's approximately and effectively 5 kilometers up. So 5 kilometers above the Earth, it's about minus 18 Celsius. That's the temperature you need for that black radiating surface to emit enough thermal radiation to balance what's coming in from the sun. Minus 18 up there. Well, okay. The next thing to observe, I think it's on the next slide, is the Earth's atmosphere, along with having a pressure gradient in it, pressure and density gradient, right? You go higher, the pressure goes down, the density goes down. It also has a temperature gradient in it. And this has to do with the fact that if you take a portion of air, a balloon, say, a balloon filled with air down here, and you drive up in the mountains holding that balloon, as the pressure drops, the balloon will expand. It started off with sea level atmospheric pressure inside, and as you go higher, that's too much pressure, and it'll push the skin of the balloon out, make the balloon swell. And for those of you who wonder what happens to helium balloons when you let go of them, they go up and they swell. They get bigger and bigger until they pop. They really do that. So alas, they don't get to travel the world. They go up and burst. So, as you go up, the air, even whether it's in a balloon or not, expands. And as it expands, it pushes the air around it out of the way. Activity that involves doing work on the surrounding air, shoving it out to make room for itself. That takes energy out of the balloon. The bubble there, is that followable? That energy comes out of the thermal energy in the air, and the air's temperature drops. So as you take a balloon up in the mountains, it will get push out on you, it gets colder. So, going up to 5 kilometers, the air will have cooled off a lot. And suppose in going up to 5 kilometers, the air will have cooled off to minus 18 Celsius. Well, that's what the temperature is up there. What temperature was it down here for it to cool from this temperature down here to get up to have dropped off, cooled off to minus 18 Celsius by the time you get to 5 kilometers? And it turns out that down here it's about 15 plus 15 Celsius. So the average surface temperature of the Earth is not minus 18 C. That's the temperature of the atmosphere located effective black body surface. Down here, we're 30 some odd degrees hotter because of this gradient in the Earth's atmosphere, the gradient of temperature. So we're about plus 15 C, which also doesn't sound very hot. Plus 15 C is like 60 degrees Fahrenheit. It's cool. But that's the average temperature over the whole Earth in all seasons, and the whole works. So that was the historical temperature of the Earth's surface before the Industrial Revolution. It was about 15 C. However, because we have been adding gases to the Earth's atmosphere that weren't there before us, before the Industrial Revolution approximately, we have made it darker and darker in the infrared. So if you compared, I'm thinking of these pictures recently of New Delhi in India, which the air is like pea soup. It is not on that extreme, but if you can see in the infrared and you look at pre-industrial Earth's air and current Earth's air, and you look in the infrared, this won't be darker. You might have to look through a significant portion of it, but it's darker. And the consequence to that is the effective radiating surface, that is what acts as a black surface in the Earth's atmosphere to radiate away the Earth's thermal radiation to balance what's coming in from the sun, that's moving to higher altitude. We're chasing it up to higher altitudes as the atmosphere gets more opaque in the infrared. And as a result, that gradient in temperature as it gets colder with altitude, it's taller. It's a taller. If we move, for example, the effective radiating surface from 5 kilometers up to 6 kilometers by darkening the Earth's atmosphere, there's an additional kilometers worth of temperature gradient on your way to warmer temperatures as you go to the surface. And that'll add about 6 odd degrees Celsius to the temperature of the surface of the Earth. That temperature gradient has some complexity in it because not only is it an expansion issue, it's also there's also water involved in it and other things. But anyway, if you raise the altitude of that radiating surface, the temperature at the surface of the Earth will increase. Questions about why raising the altitude makes it warmer down here? So that's what we're doing. We pushed it up. I don't know. I mean, I haven't tracked the exact numbers, but we've pushed up the temperature of the Earth surface significantly since we started really consuming fossil fuels. And there's sort of no end in sight at this point. And so part of modern political decisions are we going to have the guts to act and to anticipate this effect and act in advance of it actually having it develop full blown. And it's looking like the answer is no. We will not be proactive. So consequently, the temperature at the surface of the Earth is going to continue to increase as we put more and more darken the Earth's atmosphere more and more. And things that darken the Earth's atmosphere include these more complicated molecules because they need some room to move. The simple ones don't do it. So nitrogen, oxygen, not involved. The atoms like helium, neon, argon, no, not involved at all. It's the complicated ones. Carbon dioxide is bad, but far worse are things like one of the modern refrigerants is really icky black in the infrared, and there's talk of trying to replace it. It's H134C or something, or B or something. You know, we got to be careful about putting these complicated molecules up because they're long-lived and very, very dark, and you just don't want them up there in the air. Nitrogen oxides are not good. These are produced often by combustion, like cars produce them. Methane is not good. Methane is natural gas. Once you burn it and it becomes water and carbon dioxide, it's less bad, but methane itself is crummy. And it's produced, I mean, one of the sources of it apparently is cows chewing their cud and digesting the cellulose. Remember I told you cellulose is a sugar polymer that's tough to crack apart into sugars. And so they do it in their multiple stomachs with the help of microorganisms. Some of the microorganisms that they have, instead of metabolizing the path that helps the cow, they just simply turn it into methane. And so they basically burp up methane, and that is not so great. So controlling these, trying to get them less and less of that stuff in the air, is important to this heating mechanism. And okay, just to talk about some of the consequences of the heating process is, it talks about that people can live in environments that are pretty hot as long as we can give up heat fast enough that we don't overheat. And that means that when the air is above a certain temperature, we have trouble simply losing heat by the good old-fashioned process of heat flowing from hotter to colder. If the air is hotter than you are, it's not going to go from you to the hot air. It's going to go the other way. What do? Sweat. In which case you lose heat not by the transfer of heat simply from you to the colder object, but rather by evaporating water. And that will save you up to a certain temperature, but not beyond that. If the air is too humid or too hot, you can't lose heat that way. And so you overheat. So certain parts of the earth may become uninhabitably hot. That is, if the air, you can be in there if they're air conditioned, but if the air conditioning breaks down, it's not a question of whether you're healthy or unhealthy. You can't survive there. So we may lose places to that. And the other thing is well, just in general, having things get hotter is disruptive. But sea level rise, part of that comes from the melting of ice that is trapped, of water that's trapped as ice. But the other thing is that as you heat things up, they expand. With very, very rare exception. I've talked a little bit about thermal expansion, that two atoms that are bound to each other as a molecule, if you add thermal energy to them, they can begin to vibrate about the equilibrium. And they spend more time, on average, at greater separations in equilibrium than they spend at separations less than equilibrium. As a result, systems that have molecules and molecular structure, they tend to expand as you heat them. Higher temperatures makes them bigger. And the Earth's oceans expand as you heat them. So increasing the temperature of the oceans will make the water bigger, and it will fill the basin deeper. So the water levels rising for both because there's more water available with melting ice caps, and also because the water expands and it fills the oceanic basins more effectively. So think before you buy oceanfront property at sea level plus 1 or 2 feet, unless you want to be walking around in wading shoes or something. Okay.